In August 2024, a team of researchers at Northwestern University released a paper that quietly challenged one of the oldest assumptions in construction. There was no announcement of a revolutionary synthetic material, no unveiling of a complex industrial process. Instead, the method was almost unsettlingly simple. Ordinary beach sand was saturated with seawater, and a mild electrical current, just 2 to 4 volts, weaker than a standard AA battery, was passed through it. Within minutes, the loose grains fused together into a dense, rock-hard mass. No cement, no extreme heat, no industrial mixing, just sand, seawater, and electricity. What emerged was not merely hardened sand, but a transformation into something structurally solid, cohesive, and remarkably similar to natural stone. It wasn't manufactured in the traditional sense. It was grown from minerals already present in seawater. The lead researcher described the moment of discovery as watching the impossible unfold in slow motion. The sand didn't simply compact, it became a new material entirely, formed through a process that mirrored natural geological and biological systems. The findings were published in a respected peer-reviewed journal, validated by experts and backed by credible institutions. Yet, despite its significance, the discovery barely made a ripple outside academic circles. While the world continued purchasing conventional construction materials at around $30 per bag, this breakthrough sat quietly in scientific archives, raising an important question. How can something so potentially transformative remain almost invisible to the industries it could disrupt? To understand this, the story stretches back decades earlier to 1976, when an architect experimented with a similar idea beneath the ocean surface. He wasn't a chemist or a materials scientist, which may explain why he approached the problem differently. He looked at coral reefs, structures stronger than many forms of concrete, and asked a question that few engineers had seriously considered. How do these natural formations build themselves? Coral reefs thrive in harsh marine environments, growing stronger over time, repairing damage, and constructing massive structures using nothing more than seawater and biological energy. The experiment that followed was simple but profound. By placing metal electrodes in seawater and running a low-voltage current between them, minerals dissolved in the water began to precipitate and deposit onto the structure. Calcium carbonate, magnesium compounds, and other minerals accumulated layer by layer, forming a solid mass. This process, later known as mineral accretion, effectively replicated what marine organisms had been doing for millions of years. The resulting material demonstrated compressive strength comparable to conventional concrete used in sidewalks and basic foundations. It could be shaped, scaled, and even powered by renewable energy sources like solar panels floating above the water. Over time, hundreds of such structures were built around the world, primarily for reef restoration. They proved durable, environmentally beneficial, and cost-effective. Yet despite decades of evidence and validation, the construction industry largely ignored the technology. This indifference becomes more striking when placed against the scale of the modern cement industry. By 2024, the global cement market had reached over $47 billion, while the broader construction materials sector exceeded $1.8 trillion. Concrete has become so deeply embedded in infrastructure that its presence is almost invisible, even as its impact grows. The scale of its use is staggering. Humanity now pours more concrete every 3 years than was used during the entire 20th century. Entire nations have undergone rapid expansion fueled by cement consumption on an unprecedented level. But hidden within this growth is a significant cost, one that is rarely emphasized in financial reports. Cement production accounts for approximately 8% of global carbon dioxide emissions each year. Producing a single ton releases around 900 kilo of CO2, not because of inefficiency, but because of the fundamental chemistry involved. The process requires heating limestone to extreme temperatures, and that reaction inherently releases carbon dioxide. There is no version of traditional cement that avoids this outcome. Efforts to reduce emissions have focused on incremental improvements, carbon capture, alternative materials, and efficiency gains, but none address the root chemical limitation. Meanwhile, the electrical sand solidification method offers a striking contrast. The cost to treat 1 cubic meter of sand using this process ranges from $3 to $6 compared to up to $70 for conventional materials and similar applications. This is not a marginal improvement. It is a dramatic shift achieved without combustion, mining, or complex supply chains. The science behind this transformation is both elegant and powerful. Seawater is rich in dissolved ions such as calcium, magnesium, and bicarbonate, the same elements used by marine organisms to build shells and reefs. When a low-voltage current is applied, it alters the local chemistry near the electrode, increasing the pH and triggering mineral precipitation. These minerals crystallize and bind sand particles together, forming a solid matrix. The result is material that closely resembles natural stone, created under ambient conditions without extreme heat or pressure. What makes this process even more remarkable is its reversibility. By reversing the electrical polarity, the solid structure can dissolve back into sand. This introduces the possibility of programmable infrastructure, structures that can be built, modified, or removed without demolition or waste. Considering that the global construction sector produces around 1.3 billion tons of waste annually, such a capability could fundamentally change how we think about building and rebuilding. Parallel to this development, another field has been exploring a similarly radical approach using biology instead of electricity. Through a process known as microbially induced carbonate precipitation, specific bacteria are introduced into sand along with nutrients. These microorganisms produce enzymes that trigger the formation of calcium carbonate, binding the grains together. In large-scale tests, this method has produced materials with strengths reaching up to 12 megapascals, comparable to certain types of concrete, all without high Harart or emissions. Both approaches, electrical and biological, are rooted in the same principle. Nature already knows how to turn loose particles into solid stone. The challenge has always been replicating these processes at a human timescale. What recent research demonstrates is that this barrier has been overcome. With minimal energy input and simple systems, materials can now be grown rather than manufactured. This raises important questions about the future of construction. The cement industry has played a crucial role in building modern civilization, enabling infrastructure that supports billions of people. It is not a villain in a simple narrative. However, the environmental cost, financial burden, and inefficiencies associated with current methods are becoming increasingly difficult to ignore. When compared to processes that require only seawater, sand, and a small amount of electricity, the contrast becomes stark. Coastal regions provide a particularly compelling case. Nearly 26% of the world's beaches are projected to disappear by the end of the century, while over 40% of the global population lives in areas vulnerable to rising sea levels and erosion. Traditional solutions involve expensive seawalls and cement-based reinforcements that can fail under extreme conditions and harm marine ecosystems. In contrast, electrically grown structures can be powered by renewable energy, produce no toxic byproducts, and even be reversed if needed. Existing projects have already demonstrated long-term success. Reef restoration structures built using similar principles have remained intact for decades, growing stronger over time and supporting diverse marine life. They were constructed at a fraction of the cost of conventional barriers, offering both environmental and structural benefits. At its core, this entire field of research challenges a deeply ingrained assumption that building durable structures requires burning materials at extreme temperatures. That assumption is no longer absolute. The evidence now shows that solid, load-bearing materials can be created using processes that mimic nature, operate at low energy levels, and significantly reduce environmental impact. The real question is not whether these methods work. They clearly do. The question is how long it will take for them to move from the margins of research into mainstream application. Industries built on established systems rarely change quickly, especially when billions of dollars are involved. But history shows that once a more efficient, cost-effective, and sustainable method gains traction, adoption can accelerate rapidly. For now, the knowledge exists, accessible to anyone willing to look. The idea that the ocean already contains the raw materials needed for construction is no longer theoretical. It has been demonstrated, tested, and verified. What happens next depends on whether this knowledge remains confined to academic papers or begins to influence how the world builds its future.